Hi everyone, my name is Hasan. I'm a third year PhD student at Max Planck Institute for Software Systems. I'll present our work on testing action policies titled as Metamorphic Relations via Relaxations. In this work, we developed an approach to obtain oracles for testing action policies. This work is published in ISSTA 2022. So I'll be presenting it there as well in 2-3 weeks. Registration is free. You can go register and listen to me there as well. This is a joint work with my PhD advisor, Maria Christakis, and several other collaborators. Okay, let's get started. As you may know, action policies represented by neural networks are highly successful in many complex sequential decision-making problems, such as robot planning or game playing. So traditionally, once the policy has been learned, you feed it with states to obtain the next predicted action. However, in some complex domains, or like safety critical domains, a misprediction, or speaking from the software engineering perspective, bugs in action policies might result in severe consequences. Therefore, action policies has to be characterized by high degree of dependability before they go into the production. So a testing is a natural paradigm to answer this, to address these concerns. So what's a bug in an action policy? This is the first question that we should answer, and a natural answer to this question is satisfying a failure condition. For example, losing the game, crashing into other cars, or in general satisfying the task in the environment. However, consider a state where the failure is unavoidable. Can we blame the policy for the failure in this case? Of course, no, because if there is no way out from the failure from a given state, then that's not the problem with the policy. So we cannot consider such a situation as a bug. So we could ask whether a failure is avoidable or not in a state, but we could ask the optimal policy to decide this. But as you can guess, computing the optimal policy is not scalable in many cases. So far in the literature, this has to be okay. No problem. These kind of problems are considered in the literature as well, but they implicitly assume that the avoiding failure is always possible. So this was their shortcoming. And also there is a large body of work for testing neural networks. So as probably the audience is not coming from the software engineering or testing background. So probably you are mostly like AI people. So I want to give a bit of background on this literature testing of neural networks. Since the increasing popularity of neural networks, people started applying software testing and verification techniques for testing or verifying properties in neural networks in last like 3-4 years. So people develop coverage criteria or like test input selection methods, or they try to verify properties on neural networks and so on. And they use software testing and engineering or program analysis techniques to do this kind of things. So, but so far in the reinforcement learning side, there was not much such work. there were works that focus on safe reinforcement learning that aims to train neural networks that train RL agents that satisfies a given, let's say, an LTL, linear temporal logic constraints and so on. But testing of RL agents is not, as far as we know, is not studied. There are actually only 1-2 work, including this 1-2 work in this area. So so we can say that this is one of the first works that focuses on testing, like characterizing the dependability of the RL agent. So the difference between the testing neural networks and RL agents is that in action policies, assessment is done after a sequence of decisions. Like we start from a state and then we decide, usually we decide whether the agent satisfied the task only after taking a sequence of predictions. But in neural networks, a single invocation is enough to make the assessment. So usually neural network testing works are not applicable to this area. So this problem has unique challenges. So I mentioned the bugs in action policies and the shortcomings of prior work. So this is the bug problem that I mentioned earlier is somewhat similar to the Oracle problem in software testing. So whether the failure was avoidable or unavoidable, we need to know that. And this is similar to the Oracle problem in software testing, where the question is, given a test input, what would be the expected output of the program under test? So we have a program at our hand and we want to test it. So we have a test input. We need to know the expected output of the program for this test input, for this particular test input, to benefit from that. If we don't know the output if we have no idea about the expected output of the program for this test input, then it's simply useless, right? So so this is called Oracle problem in software testing. So there are many solutions developed for this problem. Among them, metamorphic testing is one of the most popular ones. So according to it, we define a relation over the inputs, define a metamorphic relation over inputs, and a corresponding necessary relation over outputs. So let's consider I1 and I2 satisfying some metamorphic relation. We feed the program P with I1, we obtain O1. We feed the program P with I2, we obtain O2. And in the end, we check whether O1 and O2 satisfy the corresponding necessary relation over outputs or not. If not, then we say that program P contains a bug. For example, coming back again to the action policies, consider the autonomous vehicle, where the input is the weather condition and the output is the speed. The prediction is the speed of the car. Let's say we have a sunny condition at one hand and a rain condition in the other hand. And in the output, the corresponding relation is that speed of the rainy condition should be 25% lower than the other case. Yeah, so this is how we handle the Oracle problem in software testing. But how do we combine metamorphic relations in general sequential decision-making problems? So what could be a metamorphic relation in this context? So for this, we consider relaxations, which is a widely studied concept in planning community. And according to it, assume we have states S and T that are related in terms of a relaxation relation, which says that T is easier to solve than S. So if this is the case, we can simply say that if the policy fails on easier state T, but not on harder state S, then we know that policy pi contains a bug manifested on T. And since we can say that relaxations provide a means to specify metamorphic relations, thus to obtain oracles. So this is how we obtain oracles in this work. So in this work, we focus on state relaxations. For example, given a state, if the obstacles need to be avoided in the environment, we can remove obstacles in the state. If the resources are limited, we can increase the resource availability, or if there are time constraints, we can postpone the deadline. And there are many other relaxation possibilities based on the environment and the task. So in this work, we consider manual relaxation design. However, as you may notice, relaxations are decided in very, very high level. So like relaxing the time constraint or increasing resource availability and so on. So almost no domain knowledge is required. So let's concretize the relaxations that we considered in this work. So we have case studies. The first one is called highway, where the task is to reach the end in a 2-lane street with traffic. So, so the relaxation is achieved by removing a car in the street, or we can simply unrelax the state by adding a car to the street. So if this is the state S, then and our agent is the red car, we can remove a car and then in the street and relax the state, obtain the relaxed state T. And the next is a OpenAI gym environment lunar lander, where the task is to land the agent on its legs. And relaxation is achieved by decreasing the height of the landing pad because simply the agent has more time and space to arrange the balance. So if this is state S, this is the relaxed state T. So we say that if the agent is winning in the state S, but failing in the state T, we say that there's a bug in the policy. And third case study is called bipedal walker. It is again OpenAI gym environment, where the task is to move a bipedal robot forward till the end of the terrain. We relax or unrelax the state by making the terrain smoother or rougher. So, for example, if this is the state S, this is the relaxed state T. Again, if the policy is winning in state S, it also has to win in the state T. If it's losing on state T, then we say that there's a bug in the policy. So this Oracle design is actually only a part of a larger scale policy testing framework called l-fuzz. l-fuzz takes a policy and an environment as input, and it has two main components called fuzzer and Oracle, where the fuzzer is responsible for generating a diverse set of pool states, and Oracle makes use of those pool states to identify bugs in the policy. l-fuzz is implemented as a generic policy tester, and it's independent of any specific environment. So it's actually quite modular, so that you can add a new environment and policy to test. It's also publicly available at GitHub in this link. I encourage you to go download and play with it. Also, please give stars. Okay, so after giving this short overview, I want to continue with a bit of formal details. So let's formally define what is a policy bug. M is a Markov decision process, and we consider E is a simulator of the MDP, and pi is a policy, and S is a state. We say that S is a bug in the policy if the probability of failure. So this is how we denote the probability of failure, is a higher probability of the failure of the policy on S is higher than the probability of failure with the optimal policy. So we also consider, so this is for the bug definition was for the stochastic environments. We also consider the seed bug, where we set the random seed to a particular value, and we run the policy on the environment where the random seed is set. So we say that we have a seed bug if the policy is failing on state S, but there exists a policy, some other policy where it can which can succeed in the same state. Yeah, so these are the definitions of the bugs and the seed bugs. So let's continue with the formal definition of the state relaxation. We say that again, consider the same definitions of the MDP simulator and the policy. We say that state T relaxes state S if for every policy pi S which succeeds on S, there exists a policy pi T which also succeeds. So it simply says that the policies in the space of policies, the policies that can succeed in state T covers the policies that can succeed in S. So that's why state T relaxes state S. It's more relaxed version of state S. So as you have seen before, if this is the state S, then this is the relaxed state T. Okay, let's continue. So after these definitions, so I gave you the idea with the metamorphic oracles, but there are options to define different kinds of metamorphic oracles actually. So we define actually several oracles. The first one is called bug oracle. So first we evaluate the probability of failure of the policy pi on state Si. So so simply let's begin with the inputs of the oracle. So oracle is actually taking the relaxation function as input, the policy, and the state as input. So these three are the inputs to the oracle, and we evaluate the policy pi's probability of failure on state S. So how do we evaluate? We simply make multiple runs over the state with different random seeds in the environment. Then we check in how many of those runs we encounter the failure. So this is how we evaluate the probability of failure of the pi. And we have a budget. But before going into there, we obtain an unrelaxed state T. So Si is relaxing Ti. So S is actually, in this case, it's inverse from the, it's reversed. It's not the same as the examples. So this had to be reversed here. So we obtain an unrelaxed state, which is a harder state, T. and we evaluate the probability of failure on that state, and we check whether the probability of failure is higher in the SI, which is the easier state. So simply, if the in one sentence, if the policy has higher probability of failing on the easier state, then we say that there's a bug. We return the bug, and then that's it. So we repeat this process with a limited budget. It's called Oracle budget. And if we cannot encounter this violation, then we return 0, which refers to that we cannot find the bug. But of course, it's not guaranteed that there is no bug in this state. But when we return 1, there's no possibility of the false positive. So it's when we return 1, it's always 1. So it's always there's bug. Next, we consider the seed bug oracle. So the first one was the bug oracle. The second one is the seed bug oracle. It's again the same logic. We again obtain a random unrelaxed state T, and we check whether the policy is succeeding in the unrelaxed state T. So this, of course, there is this if condition in the beginning which checks if the policy is failing in the easier state S. If not, then we can simply say that there is no bug that we can identify. I hope it's clear. Let's continue with the next oracle. This is again the same logic, but we don't unrelax here, but we relax this state. So T is in this case is the easier state. So we don't stop if you look at the if condition in the inner if condition, we don't return the bug, but we keep adding bugs to the bug set of bugs, because bugs are always happening on the easier state. According to this definition of bug, bugs are always happening in the easier state. So we are identifying bugs in different T's. So we don't stop, but we continue reporting bugs in this case. So if you look back in the basic seed bug oracle, the bug is happening in state S here. So it's failing. The agent is failing in the easier state S, but winning in the state T. Then we say that there's S is a bug in policy pi. Then if we find the bug with S, then there's nothing else to do. I return. But in the extended seed bug oracle, we generate relaxed states where it's failing, and if the agent is failing on those relaxed states, then we say that the relaxed state T is a bug in the policy. So we can find many different relaxed states. So we keep adding those in the set of bugs. Okay, so I also want to talk a little bit about the fuzzing. So Oracle is simply making use of the states which fuzzer finds in the state space. So we don't want to test only the initial state, but we want to test also deeper states, because we want to test we want to test the policy as much as possible, as smart as possible. So it's not so for this we developed fuzzer component. In the worst case, we could use only the initial state distribution as the state generator that Oracle will consume. But fuzzer is a bit more complex component, where we take random walks from the initial state And then if they are like interesting in terms of a diversity perspective, we add them in the pool. If not, we can discard them. So I won't go into details of this pseudocode because I don't want to lose you. But what I'm going to tell is that with Fuzzer we aim to find a diverse and interesting set of states that needs to be tested. So for this, we consider the diversity filter. So again, I want to give you a bit of background on the fuzzing in software testing. So fuzzing is a quite popular technique to find vulnerabilities and bugs in software, and it's usually consider there's a pool of test inputs. The fuzzer picks one of those test inputs from the pool, mutates a little bit based on some algorithm, or maybe it could be random, whatever, and feeds the program with the mutated test input. And if there's a crash, it's good. Like if we find a bug or vulnerability or whatever, it's good. We can report the bug. If not, it can still be good. We can still make use of this test input if it's satisfying some constraint. Let's say in coverage guided fuzzing, it is coverage. So if the newly mutated test input is achieving a new coverage, then it's also valuable because it increases the confidence in the testing campaign. So if the as I said, if the mutated test input is increasing the coverage, you add it back to the pool of test inputs, so that in the next rounds you can pick it again, mutate again, and then you can achieve new coverage. Yeah. So this is called like coverage guided fuzzing. So you keep the test inputs that increases the coverage, so that you achieve new coverages and then hopefully new bugs, and also you increase the confidence in the results of the testing. Yeah. So for taking this idea, applying this idea to the RL setting, we again use a coverage information to keep the states in the pool, and also we use this information to create a diverse set of pool states. So if in PyFuzz we add a state to the pool only if the distance between the candidate state and the closest state is higher than a threshold. So the state is defined over a set of real or integer values, whatever. So we measure the distances and we add it to the pool if it's higher than a threshold. Because state space in many complex games is almost infinite, right? So it's not possible to test every state. So we need to find a smarter way of testing the agent in the state space. So let's continue with evaluation. So I want to go back again the evaluated oracles. So these three oracles are the ones that I presented earlier. Failure seed bug is simply reports a bug whenever the agent fails. So it simply does not recognize whether the failure was avoidable or unavoidable. Rule suite bug reports a bug based on some heuristic rules, and it's actually representing the closest related work. Perfect bug and perfect seed bug provides exact measuring lines, and it's tractable only for highway domain. but we also run a limited budget perfect bug oracle in lunar lander domain, which I'll show you. MMC bug to bug is a proxy for the bug oracle that I will mention later. So you see here one plot for each domain. What I want to emphasize here is that perfect seed bug, the blue and cyan line, and the red line are almost indistinguishable. Again, perfect bug and metamorphic bug are also almost indistinguishable. Yeah, so the failure seed bug, so bug oracles and the seed bug oracles are not directly comparable. So if you compare if you check the failure seed bug line, which is the orange line, it's reporting many false it's reporting more bugs because it's also reporting many false positives. If you check the rule seed bug, which is the purple line, it's missing many of the true positives. So MM seed bug extended version is naturally finding many bugs. Yeah, in the next lunar lander and the bipedal walker, we observed a similar trend. Yeah, in the lunar lander, we ran limited budget perfect seed bug oracle, and we observed that at least 50% of the bugs reported by the failure seed bug oracle are actually not bugs. They were actually unavoidable failures. So metamorphic oracles are highly useful for identifying bugs in policies because they are superior to the rule-based and failure-based alternatives, and they are close to the perfect oracles. In the next, I want to shortly talk about the run times. As you may notice, seed bug detection is very fast, but you might be missing bugs. And the fuzzer, I don't want to discuss much. So in conclusion, testing action policies for avoidable failures requires oracles because, as you have seen, like simple or dummy oracles like failure oracle or rule-based oracles are not capable of handling this, are not capable of testing the policies as required. So in this work, we have shown a way to obtain oracles from relaxations, and we adapt the ideas from metamorphic testing, and we have shown that they are actually quite useful. And in the future, we want to explore the automated design of state relaxations, and we want to close the loop by retraining, by feeding bug states back into the area. And we think that there are many interesting opportunities in this direction. So this concludes my talk. I would be happy to take questions and comments and feedbacks and so on.
Thank you, Hasan. It was really good presentation. Thank you for that.
Thank you.
And I have some questions actually. So, first of all, I want to ask about the fuzzing things, the fuzzer. So these are all new things to me. So I'm not really, I don't really know about the testing and fuzzing, and testing in RL is all new things to me. So I just want to ask about, you said something like distance metric for fuzzing. So you need to have more coverage while finding new states, right? Something like this. So fuzzing. So if I miss, sorry, but what is the distance metric you use to find that?
Yeah, coverage? in this one we had the opportunity. In this one we simply measured the distance between states. The distance is is in terms of L2 metric. We could also these are neural network action policies, right? We could feed the state to the neural network, and then we could obtain the output of some hidden layer, and we could compare the outputs of the hidden layers, so that because in the input the features are quite raw, so they are like they're like too fine grained, let's say.
Yeah.
Once you feed it to the neural network, in the higher layers you obtain some like high level features, right?
Mm-hmm.
So we could compare the distance between the hidden layer outputs. This was also an opportunity, but we kept it simple as a first step, and we only measured the distance between the states, like and it's L2 distance.
Yeah, you mean by state you keep states in some vector format and you take the L2 distance, right?
Yeah, exactly.
Okay, you could also, as you said, compare the outputs of neurons, or maybe you could also embed this thing into the neural network and learn some new distance metric, things like that.
Exactly.
Okay. Okay, thank you. I have some more questions, but Barry, if you have questions, you can go ahead.
Thank you for the presentation. Maybe I missed the part about Oracle budgets. Can you explain what are the specifications related to Oracle budgets?
An Oracle is taking as a state a policy and the relaxation function as input, right? So we they're actually and then let's consider the bug Oracle. We find an unrelaxed state T, right? So there is not one unrelaxed state T. So there are actually sometimes infinitely many unrelaxed state T for the given state S. So we pick one of them randomly. So for, let's say, considering the highway, I could add a car to any location in the street. So this can be many locations. So I could add 2 cars, I could add 3 cars, and whatever. So these are like many possibilities of generating a unrelaxed state T. So I cannot for some domains I cannot cover all those unrelaxed state T's. So I need to explore only some of them. So this is why I have a budget, and only I generate unrelaxed states as long as my budget allows me.
Okay, thank you.
So here the random state is the fuzzing thing, right? So you generate some states.
So sorry, I didn't get
this random state. It generates some. So first of all, I need to. So there's some confusion. Is the S the relaxed state or unrelaxed?
So for the bug Oracle,
yes.
So the second parameter to the for the right side of the relation is corresponding to the easier state. Okay. Always
easier state.
Yeah, the relaxed one.
Okay, so SI is the relaxed one.
Yes. So TI is the unrelaxed one. So I get the SI as input, and then based on this, based on so among the all TIs that satisfies this relation, I pick one of them randomly.
So, right. So, and let me just see. So in the first one, you evaluate the failure of the relaxed one, and then you randomly choose unrelaxed states as you explained to Barrett. Then you calculate you compare them to obtain some bug, right? In the first one.
Yes,
Okay.
yes, exactly.
And okay. So in the other one, so in the first one, you starting from the relaxed one, and in the extended version, you at all times you start from the relaxed one and generate some unrelaxed one. Okay, so
No, the extended one is the inverse.
Inverse. Okay.
Yeah, I start from the unrelaxed one, and I create relaxed states. And the thing is that the bug is happening on the relaxed state always. So in the bug oracle and the bug seed bug oracle, once I encounter the violation of this condition, like if the inner if is satisfied, if inner if condition is satisfied, that means that I find the bug. I found that S is a bug in the policy, so I don't need to go further. So I already found that S is a bug, so there is nothing else. For the extended version, I take the S as the base, and I generate relaxed states, different relaxed states. And when I find the violation, I report it, and I add it to the set of bugs.
Oh, okay, I get it now. Okay, thank you. So, these functions have different purposes then. So,
Yes.
Okay.
Yes. Okay. Yeah. So these. So in the bug oracle and seed bug oracle, we only test whether the states in the pool are bugs. In the extended seed bug oracle, we start from the pool and then we explore the relaxed versions of them and report the bugs there.
Cool. Thank you. Better.
I have no other question.
I may ask, so I didn't understand something at the beginning. So at the beginning, you talked something like AI pipeline things in the second or third slide, I don't know. But in the prior, yes. So here, in the first part, there is large body of work for testing neural networks. In action policies, assessment is done after seconds of decisions, as opposed to single invocation and end tasks. So what does it mean, and what does it correspond to the other parts of the presentation? So, I didn't understand this part.
So for example, in the neural network, so let's consider an autonomous vehicle. I gave you this example, right? So let's say the autonomous vehicle did not satisfy this metamorphic condition, metamorphic relation, and it only lowered the speed by 10%, not 25%. So should I go crazy and let's say can I say that I cannot trust this autonomous vehicle? I think no, because it's only one scene, one step, one prediction. Maybe
that
in the
would be
next
too much.
step, maybe in the next step, in the next so in the autonomous vehicles, they the camera is let's say camera is processing images every second. Okay, maybe it made a wrong prediction in one image in 1 second, but it might recover from that misprediction in the next second. So in the neural network testing, they always consider the current neural network testing works are usually focusing on classification tasks, where everything is decided in one go. You feed the input with an image, and you decide whether the correct class is labeled predicted or not. So that's it. But in the autonomous vehicle, or in the action policies, like the sequential decision making problems, you assess in the end, like you take actions, and then you check whether the task is satisfied or not. Maybe although the autonomous vehicle made a few wrong mispredictions in the over the way, it might still reach you to the endpoint safely. So that's the difference that I wanted to I wanted to make you notice.
Okay, I got it now. Thank you so much. Okay, that's better.
Yeah.
Okay. Any question? No. Thank you so much, Hasan.
Okay, I hope you liked
Thank
it.
you.
Yeah,
Yes.
that was perfect. So very eye-opening for me. It was
For me as well.
Yeah, thank you so much.
Okay, then I stop share. You can also go read the paper and also attend the actual presentation in the conference because it's free, as I said.
Ah, nice.